Thank you, everybody. My name is Santiago Balseiro. I'm going to present optimal mechanism for value maximizer with budget constraints via target clipping. And this is joint work with Yuan, Deng, Jieming, Vahab, Mirrokni, and some two all from Google Research. Now, the motivation from this work comes from internet advertising markets where buyers are increasingly adopting automated bidders to buy opportunities. What automated bidders? Well, they simplify the procurement process by allowing advertisers to specify high-level goals and then bidding on behalf of them on the advertising options. Now, current options, the one that we're implementing right now, are not taking into account the advertiser's goal and the information structure. So then as the market is adopting automated bidders more and more, it's important for us to understand how do we sign auctions, revenue maximizing auctions in the presence of such bidders. Now, one popular strategy that you use quite a bit in practice is this target return on spend bidding. Now, what's the idea of target return on spend bidding? Advertisers specify a target return on spend for each conversion and a total budget. And then the auto bidder is going to go ahead and choose the bid to solve this problem. It's going to try to maximize the expected number of conversions, subject to two constraints. First, we have a constraint that the return on spend, the total number of conversions over the payment, is above the target. And the other one is that the payments are above the budget. And these constraints work well together because the budget constraint limits your exposure, how much you pay, and the target return on spend guarantees that you get like a good bang for the buck. Now, how is this problem different than traditional mechanism problems, and notably different with manual bidders? Is that here the objective, if you look at the objective, this is what is called like value maximization as opposed to quasi-linear utility, because we are not taking into account payments in the objective. Buyers are just maximizing the total number of conversions, and then payments are indirectly captured in the constraints. And then in terms of the information structure, now in this line of work, what we assume is that values or conversion rates are public. Why? Because in many cases, auto bidders are using the prediction technologies developed by the platform. So then from the perspective of the sellers, conversion rates are known. Now, in return, what we're going to assume is that the target return on spend, the right-hand side in this constraint, is going to be private. And this, the motivation from this assumption is that the target return on spend depends on how advertisers internally evaluate their campaigns. And then this depends on the internal accountant, which is private information. Now, what's our main contribution? We present a general model that can accommodate the complexity of the auto bidding procurement process. We reduce this problem to a problem with monotonicity constraints, which we're going to explain, and we provide a novel decomposition approach to characterize an optimal mechanism. And the structural insight is that the optimal mechanism has this target clipping structure. I'm going to explain this later, but the main idea is that we have a threshold. Above the threshold, we allocate efficiently. Below the threshold, we clip all the buyers to the threshold, and they get the allocation at the threshold. Okay. Now, in terms of related work, there is like a very recent line of work on auto mechanism design in the auto bidding world, looking at price of anarchy of different options, trying to incorporate ML advice or doing Bayesian mechanism design. And also we build on work on mechanism design with constrained buyers. People have looked at budget constraint and return on constraint in isolation too. Now, the outline, what I'm going to do today, I'm going to talk briefly about the model and the mechanism design problem. I'm going to explain our reduction to a problem with monotonicity constraint. I'm going to give you like a preview of the single buyer case, and then I'm going to go very quickly over the multiple buyer case for you to understand the main challenges that arise there. Let me start with the model. So we have like n bidders. Each bidder has a target, tau, that's going to be a private target drawn from a distribution, and BI, a public budget. Now, the seller is going to implement an alternative. I'm going to explain what an alternative is going to be shortly, but you can think about this could be the outcome of an auction or an allocation. And it's going to have a cost function that's going to determine what's the cost of implementing this alternative. The buyers are going to have like a public valuation function that is going to map this alternative to the RIA. It's going to tell how much value they get. That's going to be, for example, the total expected number of conversions. And we're going to focus on direct mechanism. What's going to be a mechanism? A mechanism is going to have two components. It's going to have an allocation X and a payment P. And it's going to take reported target from the buyers. This is going to be the private information. And based on the reported target, it's going to choose an allocation. There's going to be a lottery over the alternatives, and it's going to choose a payment for each of the buyers. And the buyers, in turn, are going to solve this problem. So the buyers are going to be value maximizers, as we mentioned, with a return on spend and a budget constraint. So you're going to maximize expected values subject to the return on spend constraint. So here we linearize it, but it's the same ratio constraint that we had before with the target, and that the payments are most the budget. And here the point that I want to emphasize, and this is going to be the same in the following talk, is that constraints are soft. Here we are interpreting constraints as an expectation over the lottery of alternatives, and this takes into account that in this market you participate in many different auctions, for example, and then you impose constraints in expectation in a soft way. So what's an alternative? So far I was very vague on alternative. You can think of an alternative as the outcome of a matching algorithm or running multiple sequential auctions, the outcome of an online optimization algorithm. Again, our model is quite general. Let me give you some concrete example. So one concrete example is stochastic allocations over bipartite graphs. This is like very relevant for advertising markets. So we have like a bipartite graph. On one side, we have the buyers, and on the other side, we have the impression types. These are going to be the users that are connected. Each impression type comes with a probability Qj, and then when we have a type J, Wji is going to be the conversion probability. What's going to be the probability that somebody converts if we show this impression? To this impression, we will show this buyer. Now, what's going to be alternative? Here, alternative is going to be an assignment. It's going to tell us for each impression type, which buyer are we going to assign? And the valuation function is going to tell us for this matching, what's our expected conversion rate. And here we're saying, look, we're summing over the impression types. We multiply the probability that we have this type, what's the conversion rate, and then whether we assign it or not. Okay, so this is an example of an alternative. This alternative could be quite complex objects. Now, we're going to restrict attention to mechanisms that are incentive compatible. One incentive compatible mechanism is going to be one such that every agent is better off reporting their target truthfully, and also we're going to do it regardless of the reports of the other agents. So it's going to be DSIC in dominant strategies. So how do we write this mathematically? Let us denote that UI tau, that's going to be the expected value of an agent if everybody reports tau, and I'm using allocation X. So it's just like an expectation over the lotteries when everybody reports tau. Then each buyer should be better off reporting its target. So then it's going to be, so in this problem, look, if my true target is tau, then I should better off reporting my target. So then this is going to be the expected value I get, subject to the budget constraint and the return to spend constraint. And then if I optimize over every other target tau hat, then the optimal should be to report my target truthfully. So here we allow, again, for deviations that are constrained to the budget and the return on spend. And what's the objective of the seller? Well, the seller is choosing a profit maximizing mechanism. It's a mechanism that maximizes the payments from the buyers minus the cost of implementing this alternative, and the seller is maximizing over the allocations and the payments, and this needs to be IC. So this is the problem that we're trying to solve. Now, how do we reformulate the problem? Well, the main idea here is that instead of optimizing over the allocation and payment, what we can do instead is we can optimize over these expected values UI tau. And in doing so, we need to introduce two useful objects. One object is the set of achievable values. So this gives, for each vector of expected values of the buyers, it tells us whether this is attainable via a lottery of alternatives. And the other is the auxiliary cost function, and it says, like, look, if you want to implement a given expected value for the buyers, then you as a seller, with the way that you want to do it at the minimum cost. So you're saying, look, if you want to have like a given utility levels, then you better do it at the minimum cost. And then using these two objects, we can actually reformulate our problem. Now, before we're doing so, let me give you an example of this set of achievable values. So this is an example with two buyers. And then going back to this like bipartite graph, suppose that you have like two agents, and then these weights are IID uniform CO1. So then this set would look like this. So this red set would capture the set of achievable values for each point over there. Then you can always pick an assignment that achieves that value, and then we're going to optimize over this set. Now, some facts: this set is always convex because we're allowing for lotteries over alternatives, and then we're going to assume that it's downward closed, compact, and with not empty interior. So these assumptions are actually quite benign. So in order to proceed with reformulation, we need to understand what are the implications of this compatibility, when a mechanism is going to be IC only if the expected value is decreasing in the target. So it should be, if you look at your target, then the expected value you get from the mechanism should be decreasing. And this is kind of very intuitive. Why? Well, if you have a given target, then you can always report a higher target. That won't violate your constraint. So then it should be the case that that gives you less payoff. Otherwise, you may misreport. Now, you cannot report the lower target because that's going to violate your constraint. So that's why we allow your payoff to be increasing in this way. And then we can also eliminate payments. If you look closely at the budget and return on spend constraint, you're going to find out that these provide upper bounds on the payments. And then if you take the payments to be just the minimum of this upper bound, then the budget and the value over tau, then we can always choose payments in this way. And why we're going to do it? Because if we're maximizing payments, we're going to make it as large as possible. So then with these ideas, we can write the problem as follows. So instead of optimizing over the allocation and payments, now we are optimizing over these expected value functions. And then payments, we replace it using this formula. It's going to be the minimum of the budget and the expected value over the target. And now the cost, we use our cost function because at any value level, we're going to pick the minimum cost. Now, we have two constraints. IC constraint, we replace IC with this new constraint that we need this function to be monotone for each of the components. And then we have the other constraint that says that the values that we choose should be implementable. They should lie in the set because then we want to be able to pick up an allocation to implement them. Now, if you look at this problem closely, you're going to find out that this is a problem with a monotonicity constraint. Now, monotonicity constraints are pervasive in mechanism design, for example, in Myerson's problem, or also in information design. Now, the difference here is that we have like a non-linear objective, so we cannot use the standard techniques that we use in other problems, so we need to provide a new approach to tackle this sort of problems. Good. Now, two useful web benchmarks before I discuss our solution. One is the first best solution, that is the profit maximizing solution when the target ratios are known, when there's no prior information. If there's no prior information, then we don't have the IC constraint, and we're just picking for each target the optimal allocation because the problem just decomposes. So if you know the target, for each target, you're going to pick the optimal utility levels to maximize payments minus the cost. And also the other solution that is relevant for us is the one without budget constraints. If budgets are infinity, then here it will disappear, and then the payment should be just the ratio of expected values to target minus the cost. Now, one fact is that it's possible to show that the first best solution without budget is always decreasing in the target. So then we can always implement the first best solution in the absence of budget. So here, this should be actually decreasing in the target. So then we can always implement it. So then if the answer of budget, the problem is simple. You can just implement first best. But then what we see here is that budget introduce a complication in our model. And let me give you some intuition of the result. I'm going to try to do it instead of using any math. I'm going to try to do it with a picture. Now here I'm showing you for the case of one buyer. There's only one buyer, so as to simplify the problem. And I have the target here. And then this is the option that we're optimizing over, the expected value function. As I mentioned before, if we don't have any budget, then this is decreasing. So then this can be implemented truthfully. Now, when you introduce budget, we have this red line, and what's going to happen is that for low targets, the budget constraint is going to be binding, and now this function is going to be single peak. So then this cannot be implemented truthfully because remember, we need to restrict attention to solutions that are decreasing. Now, how do we do that? Let's take any monotone solution. So this is any mechanism that is IC. We're going to see that this solution can be improved in the following way. How? Well, we can always construct a solution that is going to be constant first up to reaching first best, and then it's going to trace first best from then on. So the optimal solution always going to have this structure. Why? Well, so if you look at this solution green, and then the new solution that I give you, if you look at this point at tau hat, then to the left, if you move downwards, you're always closer to first best. So then this is going to improve your profit. And to the right, if I move it that way, you're always closer to first best too. And then also it's going to improve the profit. And here you're just tracking first best. So this is the best that you can do. And this solution that I constructed by virtue of my construction is always going to be monotone. So it's always going to be IC. So if I give you any solution, then I can always find these points and then trace a new curve that is going to be piecewise constant and then track for best that is going to do better. So actually, we can show that the optimal mechanism has this structure that is going to have like a threshold, tau bar. To the left is going to be constant, and to the right is going to track first best. And this is like the first result. There's always exists an optimal solution, what we call a clipping threshold, this tau bar, such that to the left is going to be constant, and to the right you track first best. And this is some sort of non-linear ironing procedure. So just to kind of emphasize this point, what we're going to do is we look at the target space and we put this clipping threshold. To the right, we allocate efficiently. Now, to the left, we're going to allocate inefficiently. And then because the respective value is constant, what we're doing is that all targets here, they're going to get the same allocation that this clipping threshold. So that's what we're clipping. We're clipping all these targets to that value over there. That's what we call it, the clipping mechanism. And what we have is the constraints. The monotonicity constraint is only binding to the left, and then we can show that the ROS constraint binds for high values, the budget constraint binds for low values, but they never bind together. Now, in the multiple buyer case, the things get a little bit more complicated. How do we solve this problem? Well, we use the single player case as a observability block. I cannot give you all the details. Let me just give you a quick preview. For each buyer, we determine an optimal mechanism with the budget and the monotonicity constraint of all the other buyers are relaxed. So we only look at one buyer in isolation. This is going to be a single buyer problem. So then we have like this single buyer problem for each buyer, and then we combine them together into a single mechanism. Now, the challenge that emerged is that the clipping threshold now, they're going to depend on the reports of the others. And then when you combine these mechanisms, then you want the mechanism to be IC for all buyers, but then because you're only optimizing for one buyer at a time, you're not guaranteed that it's going to be IC for the other one. And the technical contribution is we provide the novel approach to using infinite dimensional duality theory to combine these mechanisms. I'm going to finish with this picture just for you to get like a visual representation of the mechanism. So this is the case for two buyers. If you first look at buyer one, and then you fix the target of buyer two. So then we are clipping to this point. And to the right, we allocate efficiently. And to the left, HN1 is clipped. If you look at buyer two, we're doing something similar. Here we clip to the threshold. And above, we allocate efficiently. Now, the only problem is in this region where the curves cross, where both HN need to be clipped. So the way that we do the clipping there is we clip it to this point, to this corner here. And then we can actually show that this mechanism is actually optimal. And with that, I'll finish here because I'm running out of time. Thank you.
Thank you, Santiago. Very good. I think we have time for one quick question, maybe. Let me just see. While we are pulling up the new slides. Right, please. Right. Do I talk for a microphone? Please, yeah, I don't think these pick up quite well.
I don't know if there's a question. I can't hear it.
Hello, can you hear me now?
Yes.
Oh, fantastic. Thank you for the great talk. You set up the mechanism design in a direct revelation sort of manner. One sort of implementation I could imagine is one where the bidders are declaring their return on investment constraints to an auto bidder, who then plays, then play against each other for like a base auction. I'm wondering if there's a way to interpret your mechanism in sort of that type of framework.
Yeah, so this is like kind of something that we have been thinking of, that we are assuming that this is direct, so it requires us changing in some sense the bidding language for people to report this information. Then if this information is not reported, then things become a little bit more complicated, and we're not sure how we can implement these mechanisms. But if you want, I can take that offline and provide you a little bit more background on this too. I don't want to take time from the next speaker. Yeah.
Okay, great. Thank you very much.